Hello, everyone. My name is Samuel Sequal. I am a quantum application scientist at INQ, and this video is to introduce the challenge problem 2025 SKKU challenge problem that I designed. The title of the problem is Simulating Fluid Dynamics on a Quantum Computer. Mainly, in this video, we're going to walk through a simple implementation of the quantum lattice-Boltzmann method for the one-dimensional adventure diffusion equation. Okay. First, it's a little bit of background on lattice-Boltzmann methods. How is it really used to solve the one-dimensional adventure diffusion equation numerically? And then, so just the introduction of lattice-Boltzmann method, and then the quantum part. The quantum implementation of lattice-Boltzmann methods involves 4 steps: initializing the initial distribution, collision, applying the collision operator, the streaming operator, and addition. So this challenge problem just walks through each of these steps in trying to implement the steps to build out the QLBM algorithm to solve the one-dimensional adventure diffusion equation. Okay. Now, the first part, this is the initialization part, as I mentioned. So here we have a state, the initial distribution, which is phi x t is equal to 0. The initialization part is just encoding the state into a quantum state. Okay, here you initialize a quantum circuit with 2 registers. Register Q for this for the distribution, and the register D for individual distribution functions, individual particle distribution function. I also give an example here to get started: a 1D lattice cell with m cells and q macroscopic velocities. And then I have a few questions here from A through C just to get started. The second part is implementing the collision operator. Now I simplify this a little bit, as you can see from equation 7. So for uniform velocity field, which is what we're going to work with, this step just amounts to preparing this state, as you can see, defined by given by equation 7, preparing this state in the direction register D. More details about how, about this process can be found in reference 2 right there in the references. So basically, and then I give an example here. In the 1D case, example problem, I give the weight coefficients for the 3 different directions, meaning staying put, going to the right, and going to the left, and then the velocities, as you can see, adventure speed. And then here, part A, you have to use Qiskit to just create a function that initializes the state, both initializes the state and applies the collision operator. Part 3 involves applying the streaming operator. The streaming operator can be implemented by using the right and left shift operators. I give a brief introduction to the right and left shift operators. So your job here is to figure out what these operators are. I give a few examples on if they act on states, what happens. So your job here is to figure out what these operators are for 2 and 3 qubits, and in general n qubits. How can they be applied to this quantum circuit that's already been initialized from the previous step? How can it be initialized to act on the correct individual particle distribution? And then part 4 is the addition part. So this is the part which calculates the microscopic density from equation 2 above. And then I give you a hint here. This can be applied by using Hadamard gates on the cubic register, on the qubits in the D register, and postulation. So you have to figure out what is the state on the D register that gives a desired state. And also here you have to figure out the right normalization from the readout. And then part 5, this is the last one. This puts everything in together. So here I'm asking part 5A, I'm asking, using all the routines you created from the above 4 steps, and just initializing the state, applying the collision, streaming, and addition. Okay, you get from the addition part, you get the phi at t is equal to 1. Now we want to use in part 5, we want to go to another step. So that was just one step. So to get to the second step, the initial state will be phi at t is equal to 1. So here, part A, I want you to repeat all the steps to get phi at t is equal to 2. In part B, I want you to repeat all the steps above for 20 steps. So simulate the fluid flow for 20 steps for the problem that I just described in the previous sections. And then in the last part, here you have to plot the states, the concentration at t is equal to 0, t is equal to 1, t is equal to 2, and t is equal to 20. That is all I have. I hope you really enjoy doing these challenge problems. I left my email here. If there are any questions about this challenge problem, you can email me directly. And thank you very much for participating.